L22 Part 2 Moment Generating Functions continued. We're going to look at the moment generating function for the normal distribution. We'll start out with a standard normal with a mean of 0 and a variance of 1. In that case, the density function is 1 over root 2 pi e to the minus 1/2 z squared. To compute the moment generating function, we do the expected value of e to the tz, which is the integral of e to the tz times the density function. We can factor out the constant 1 over radical 2 pi in front of the integral, and then we can multiply the e terms and add the exponents. And so the exponent becomes negative 1/2 z squared plus tz. And then we have to complete the square on this expression. So I'll just briefly go through that algebra. We factor out a negative 1/2, leading to this second term having a coefficient of minus 2. So we get negative 1/2, parentheses z squared minus 2tz, and then we're going to complete the square. We take half the middle term here, so 1/2 of the negative 2t, and we square that. So we're going to be adding and subtracting t squared to complete the square. And then these front terms give us z minus t quantity squared, distribute the negative 1/2 back through. So negative 1/2 times negative t squared is positive t squared over 2. So there's our new exponent now. We have a sum in the exponent, so that comes from multiplication. E to the t squared over 2 is constant in this integral with respect to z, so we can factor that out front. And what's left here is a shift, but will still have the same value as integrating the density. And so this is going to cancel out with the root 2 pi to be 1. And we're finally left with the moment generating function for the standard normal is e to the t squared over 2. Now, if we take the derivative of that and substitute in 0, we can find the mean. The derivative with respect to t is the exponential, and the derivative of the exponential is itself times derivative of the exponent, which is 2t over 2, or just t. Plugging in 0 gives us 0, which matches that the mean here was 0. Alternate approach is to express e to the t squared over 2 as a power series. The power series for e to the x is 1 plus x squared over 2 plus x cubed over 6 plus dot 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 x to the n over n factorial. Replacing x with t squared over 2 in this expression gives us 1 plus t squared over 2 plus t squared over 2 quantity squared over 2. Squaring makes a t to the 4th over 4. Divided by 2 makes t to the 4th over 8. Same thing in the next term. The 2 cubed is 8, times 6 is 48. Multiply the exponents. 3 times 2 is 6. And then you could do derivatives on this expression, or you could use the relationship between the derivative and the coefficient. And we see here that coefficient a sub n is the nth derivative at 0 over n factorial. So because we're missing the t to the first term, that's going to be telling us that the first derivative at 0 is equal to 0, which is matching what we got from before. And then if we want to look at the second derivative, we know that a sub 2 is the second derivative at 0 over 2 factorial, which is 2. And that coefficient is 1/2. So cross multiplying there, we get that m double prime of 0 is 1, which is the expected value of x squared. If we want to shift this back to a general normal, we use the z-score formula. Cross multiply, we get z times sigma plus mu to get the general normal random variable. We have to compute the expected value of e to the t times x, which is z sigma plus mu. And we can use some properties here of e and the expected value, factoring out the fixed term e to the t mu and the expected value of e to the tz sigma. That's going to be the moment generating function of t sigma, and we can just substitute that in, and we end up with e to the t mu times e to the t sigma squared over 2, which is t squared sigma squared over 2. So that's the moment generating function of a general random variable x with mean mu and standard deviation sigma squared. We can check that. If we take the first derivative here and plug in 0, we should get out the mean. So the derivative of the exponential is itself times the derivative of the exponent with respect to t. Which is mu plus 2t sigma squared over 2. 2's cancel out. It's mu plus t sigma squared. Plugging in t is 0. Plugging in t is 0 here. We're going to get e to the 0, which is 1. We're going to get mu plus 0. So the whole thing is just mu as expected. And then you could do the second derivative here to get the variance. If you have a sum of independent random variables x and y, the moment generating function of the sum is the expected value of e to the tx plus ty, which is the expected value of e to the tx times e to the ty. We can do those expected values individually, and we get the product of the moment generating functions. Moment generating function of x times moment generating function of y. So one of the useful properties here of the moment generating function works nicely for the sum of independent random variables. The moment generating function of the sum is the product of the moment generating functions of the individual variables. So if we work with a standard normal distribution here, the mean of the sum will still be 0. The variance will be 1 plus 1, 2. So if we want to get the moment generating function, we just multiply the standard normal moment generating function times itself. E to the t squared over 2 times itself is e to the 2t squared over 2, which is just e to the t squared. So this derivative at 0 should match the sum of the means, which is 0, which it does. And then the second derivative should give us 2. So first derivative is e to the t squared times 2t. Let me just write that in here. So m prime of t is equal to e to the power t squared multiplied by 2t using the chain rule. The exponential times the derivative of the exponent 2t. Plugging in 0, we're going to get e to the 0 times 2 to the 0, which is 0. Now, to do the second derivative, it's going to be a product rule here. Derivative of e to the t squared is e to the derivative of e to the t squared is e to the t squared times 2t, and then all that is times the second 2t. I think there's an error here. We don't need the t squared over 2. That was in the original, and we're working with the sum here now. So this should just be t squared. Derivative of e to the t squared is itself times 2t. Second function is 2t. And then the second part of the product rule, we're going to leave the e to the t squared alone. Derivative of 2t is t. Derivative of 2t is 2. So let me just label that here. So in the product rule situation, This is f prime and then times g plus f times g prime. And so then plugging in 0, first term drops out to 0. Second term is e to the 0 times 2, which is 2. So m double prime of 0 is 2. Then the variance is expected value of x squared minus the mean squared, which is 0. And so we'll get that 2 back. Let me just fill that in here quickly. Sigma squared is the expected value of x squared. So it's 2 minus the mean squared. So it's 2 minus 0 squared, which is 2. I'll just put VAR here, variance. Okay. All right, next up, Poisson distribution. Now, a little change here. We're back to a discrete situation, so we're dealing with a series rather than integration. The the probability mass function is lambda to the x times e to the x over x factorial. The expected value e to the tx, we're doing the sum. X goes from 0 to infinity of e to the tx times the probability mass function lambda to the x e to the minus lambda over x factorial. E to the minus lambda is a constant here. X is what's changing, so that factors out. We have an e to the tx times lambda x over e to the tx times lambda to the x over x factorial. So now we can use the exponent law here, and we can say that this is e to the t times lambda to the x power over x factorial. And then that form is the form for the power series of E. It's a little bit different. We have the X in the opposite spot, but that's the power series for E, and this argument inside here will be the exponent. So this sum is E to the power e to the t lambda, and then times the multiplier out front, e to the minus lambda. And then you can add the exponents, and it's e to the t lambda minus lambda. And you can factor out lambda in that exponent. So that's the moment generating function for the Poisson distribution. And if we take the first derivative and plug in 0, we'll get the mean. The derivative of the exponential is itself times the derivative of the exponent. Derivative of a lambda e to the t, lambda times e to the t minus 1 is lambda times e to the t minus 0. So it's just lambda e to the t. Plugging in 0 for t, we're left with lambda times e to the 0 times 1. So we get just lambda, which is the mean of the Poisson distribution. If you want to do second derivative here, I'll leave that for you to check. If you do the second derivative, it involves a product rule. And then you're going to plug in 0, and you get lambda squared plus lambda. And then plugging into the variance formula, it's expected value of x squared, which is this m double prime of 0, is e of x squared, minus the mean squared, which was the first derivative. So that's lambda squared plus lambda, minus lambda squared, and it cancels out to lambda. So let me just write that variance formula in terms of the moment generating function. So it's the expected value of x squared is m double prime. So it's m double prime of 0 minus the quantity m prime of 0 squared. So that's the variance formula using the moment generating function. M double prime of 0 is e of x squared. M prime of 0 is e of x is the mean. I just emphasize that here. So the second derivative is e of x squared. And so we ended up here with a lambda after simplifying. All right, continuous uniform random variable working with a specific example here on the interval 2, 5. The density has to be 1 over b minus a, which is 1/3. So it's 1/3, constant 1/3 from 2 to 5, 0 elsewhere. So the moment generating function now, it's continuous. So back to integration of e to the tx times the density, which is just the 1/3 constant. Integral of e to the tx is e to the tx divided by the coefficient of x, which is t. So it's e to the tx over t. And then we're plugging in the limits here, 5 and 2. So it's 1 over 3t is factored out, e to the 5t minus e to the 2t. And so you can use that as your moment generating function form, or if you want, you could use power series. One issue here with this situation is that this expression has a division by 0 in it. So we kind of have a little bit of an issue there taking the derivative at 0. So that's one benefit if we convert over to power series. A little bit tedious, but it will get rid of that division by t. So the power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So for e to the 5t, we're replacing each x with 5t. For e to the 2t, replacing each x with 2t, and then we're going to subtract them. So most importantly, those ones cancel out. 1 minus 1 is 0. 5t minus 2t is 3t. Then we're going to have 5t quantity squared minus 2t squared. 5t cubed over 3 factorial minus 2t cubed over 3 factorial, and so on. So we have the 1 over 3t is factored out. 1 over 3t is still in front here. E to the 5t minus e to the 2t. Again, just subtracting common like terms here. 1 minus 1 is 0. 5t minus 2t is 3t. And then we have the power 2, power 3, and so on. For power 2, it's 25t squared minus 4 is 21. 5 cubed is 121 minus 2 cubed. 5 cubed is 125 minus 2 cubed 8 is 117, and so on. And then we can reduce that down. And then we can see right away from either the derivative or power series, this coefficient that's telling us that m prime of 0 is 7 over 2, which for a uniform distribution, the mean is a plus b over 2. 2 plus 5 over 2, 7 over 2. Again, 2 and 5 were the endpoints of the interval we were working on here. And then to get the second derivative, we could use the coefficient formula, or we could just take derivatives here, and we end up with 78 over 6 for m double prime of 0, which is equal to 13. Again, you can do that by the derivative or using the fact that that coefficient of t squared is going to be the second derivative divided by 2. It's multiplied by 2, and we get that value. So this is expected value of x squared minus expected value of x quantity squared, which is equal to it's m double prime of 0 minus m prime of 0 quantity squared. Sorry, let me just clean this up. So this is 7. So it was second derivative at 0 was 13. First derivative at 0 was 7 over 2. So this expression is 7 over 2 squared. So it's 13 minus 49 over 4, which is 52 over 4 minus 49 over 4, which is 3/4. That's your variance. And the formula is b minus a squared over 12, which is 5 minus 2 squared over 12, 3 squared, 9 over 12, which is 3/4. And so that gives us the variance. So the moment generating function gives us a way to calculate the mean and variance. It gives us a way to calculate the sums of independent variables here. It's helpful in that way. All right, this concludes lesson on moment generating functions. As always, please don't hesitate to email or post on the discussion board if you have any questions.